on this computer.
Suffer a lot, so the defenses.
Okay. I hope I'm recording. We're recording in different places now, so that's good. I think we're good. Okay, so shall we start? I think we're on time mostly. Sorry? Perfect. Excellent. Great. All right. So everyone can hear me. Everyone can see the slides. Everything is good. And there's actually a large physical attendance. That's great. Yeah, so today, well, thank you all for coming. I'm going to talk about push-based execution in DuckDB, which is something that I have implemented maybe a few weeks ago and has now been merged. So this is all like stuff that's, well, brand new in DuckDB, let's say. So maybe before I talk about push-based execution, I'm going to talk about what DuckDB did before, which is pull-based execution. Surprise. So when we initially developed DuckDB, we used the pull-based execution model, which we like to call the vector volcano, because it's a volcano model, but instead of having individual tuples, you have vectors going through the pipeline. The way this works from like an implementation perspective is that every operator implements the getChunk method, and the query starts by calling the getChunk on the root node, and those nodes can then recursively call getChunk on children until you get to a scan, etc. You resolve it, and then you well, you get your answer, you compute your answer in a pull-based fashion. And of course, the pull-based refers to the fact that an operator does not do anything until this getChunk is called. I assume most people here are familiar with the vector, with the volcano model, so it's very similar to that. So kind of give you an idea of how this would look like in code. If you have a projection, of course, this is like simplified. What you would have is you have a child on a projection. The projection would get a chunk from the child, call the getChunk method, check, hey, am I finished or not? Like, did my child produce anything? If so, we execute the expressions that are stored in the projection, store it in the result, and bubble it upwards. For a slightly more complex example, we have a hash join. So for a hash join, what you would do is you would first check, hey, have I already built my hash table? If I haven't, I would just pull chunks from the right side and push those chunks into the hash table until the right side is entirely exhausted. Afterwards, I would pull a chunk from the left child and probe the hash table with that. And you can kind of see that in these nodes, the whole control flow, or the whole data flow, is just explicitly modeled inside each of the nodes. That's kind of like what is a nice thing about the pull-based model, is that the operators have full control about how the data moves, right? So of course, in this model, single-threaded execution is straightforward. That's also what the volcano model was designed for way back when. I don't know if it was designed by Guus Greve, but probably. Way back when it was designed for single-threaded execution. And that's what it works nicely for. For multi-threaded execution, it doesn't work so nicely. So how do you do this in multi-threaded? How do you make these operators parallelism aware? So one solution is the exchange model. We don't use that for various reasons that I've discussed before also in my parallelism talk. We use Morsel-driven parallelism. And what happens in Morsel-driven parallelism is that you make the individual operators parallelism aware. You divide the query into or the query plan, the query tree into different pipelines. And each of these pipelines, they are executed in parallel, like multiple threads can work on one pipeline at the same time. Well, there's a paper about this by Victor Leijs and such, by the Munich people. So maybe a more concrete example of what these pipelines look like. If you have a query that has like two joins in it, so we have a table S, we join with table R, join with table T. What we end up with is three pipelines. And each of these pipelines, it's no longer a tree, it's, well, a pipeline. It's just like a series of individual operators. So we end up with two pipelines that represent hash table builds, where we just go from a scan to a projection or a filter or what have you to the actual build. And we end up with one third pipeline, which then has a dependency on the other two pipelines, where we probe the hash tables, right? And these hash table probes, they just kind of like, they fit into the pipeline as individual operators as well. So using this pipeline model, we split the query tree into a bunch of like fragments of, well, a bunch of like linear fragments where we just handle a bunch of operators. So of course, you can parallelize between these different pipelines. But what you really want to have good parallel execution is you want to parallelize inside one pipeline, because what often happens is that you have one very heavy pipeline, like, oh, I want to build I want to do like a bunch of probes on like my big fact table, or using my big fact table, and I need to parallelize that. So how do you do that? Well, in a pipeline, the contention happens only at the endpoint. So in the middle, you have a bunch of nodes, like you have a hash probe, you have a filter, you have a projection. Generally, these are like just, they can be executed as is. They don't need to be parallelism aware at all, because they just take some input and modify that input. They don't have an effect on a global state. However, at the endpoints, namely the source and the sink, you do have that global state. So for example, if we have our hash table build, of course, we want to end up with one big hash table that represents the hash table of T. On the source, we have contention because we only want to scan every tuple inside T once. We don't want to scan T like 8 times. So the way that we can model this like parallelism inside a pipeline is to use parallelism aware operators at these endpoints. And then the rest of the operators, they don't need to be aware, just the sink and the source. So, well, how do we do that? Well, for sinks, we have a nice interface, or we have this interface for some time, where you have a sink, and the sink can define global and local states. Basically, you call sink until all the data is exhausted, with the global and these local states as input. Combine is called afterwards to like combine intermediate output from different threads. And afterwards, you call finalize once. So maybe a more concrete example. So this interface will be implemented by a different operator. If you have, say, like a simple ungrouped aggregate, the sink would just add to some local states, and the combine would then merge the state from different threads together, which gives you quite nice, nice parallel behavior. So the way that this then works, these pipelines, or the way this used to work, is that you had kind of this mix of a pull-based and a push-based model. Because a sink is, of course, this is a very push-based thing, a sink, you just push chunks into it, but the rest of the nodes were still all pull-based. So we kind of had this loop where you had like, okay, while I'm still pulling nodes from my child, I call the sink. After the syncing is done, I combine, then I call finalize, and I schedule my dependent pipelines, right? So if you have the hash join again, how this might kind of look is that now in the sink, you built your hash table, and in the get chunk, you do still do the control flow where you pull chunks from your left child, and then you probe the hash table that you have built in the sink phase, right? Of course, I'm leaving out a lot of like states here, etc., just like simplify. That's kind of how this would look. Now, how do we partition sources? That's in this pull-based model, it's not so straightforward because these sources, they are located like kind of in the bottom of the tree or top, depending on your perspective. So how do you get there? Because you have this like chain of get chunk calls. So our solution at the time was like medium hacky. We have like a bunch of tasks. The tasks can define how the scan is partitioned. And those tasks then reside somewhere in like a thread local context, where the thread knows, okay, I'm working on this task. And then the get chunk actually checks, hey, do I have a task for this node? If so, I actually use the task. Kind of like trying to put something, yeah, in like it's not a very clean interface, let's say. You just push the task somewhere and then read them again in your get chunk. It did work.
Sorry, what's going on here? So this is the get chunk of table scan. If the task contains this task, then I scan a task.
Yeah, so
I scan. So what's the difference here?
So the way it works to parallelize a task, the way it used to work, is that we had a list of tasks, like a map of tasks that are defined per operator, right? So we had like, oh, this table scans this partition, for example, and that's what this like scan task would do, right? So you would, instead of
what's the other alternative then? I mean, what else would you do?
The alternative is that you just do a sequential scan of the whole table instead of doing like
take the whole table.
Yeah, you just scan like chunk at a time from the whole table. Instead of, so at some point.
Okay, so the table scan tasks, the tasks are just there if you have a parallel program.
Exactly.
There are no tasks.
Yeah, exactly. That's kind of like how it was.
Basically, what happens is, well, this is a bit of a hack, because you could also say, if I don't have parallel tasks, I have an array of size 1, you know, and then tasks 0 or whatever.
For sure.
Would be the full table.
For sure.
But I think the point is that you have some kind of data structure where you have predetermined, called tasks, where you have predetermined units.
Yes. Yes. This is, in general, I think this is not very nice, like, because you don't have like an actual solid interface for these tasks. You kind of just put the task somewhere and then the get chunk reads the task again. Yes, you could also envision the other way. Like I said, this is just like a sort of sketch of how this might be implemented. So I agree, it's not very nice. But still, it mostly works. There's a bunch of problems with this pull-based model. I mean, we've been using it for like, I think it's been like more than a year since we had the parallelism. So it does mostly work, but there's like a few problems. The first, from like a code perspective, is that you duplicate data flow in every operator, which is just not very nice, because every single operator needs to like handle the data flow around it by itself, which then also can lead to sometimes the data flow being handled incorrectly, because also this get chunk, it aborts if you return a chunk of size 0, but then a filter might just return a chunk of size 0 to begin with. So then you need like a loop inside the operator to handle that case. In general, it's just not very clean, let's say. For the source parallelism as well, there's no clean interface. You just have like this sort of task thingy. And there's some other problems, like how do you, in this model, parallelize like union nodes? You could kind of envision something with these tasks again, where you have like per union task and the unions look at this. But again, it's a bit messy. How do you parallelize full and right outer joins? This is actually like a kind of a problem, because in a full right outer join, if you're not familiar with it, you basically need to scan the hash table again after you've done all the probing, right? So for the semantics of a full right outer join, you have to scan from the right side all the tuples that don't have a match on the left side, which means you have to first complete all the probing and then scan the hash table. So how do you parallelize that cleanly in this model? Then how do you do scan sharing in this model? That's also like, it's just like all fishy all down there. And async IO is of course also not very nice to implement in such a system, right? A pull-based system.
Not to mention distributed parallelism and distributed systems where you have the same kind of issues.
Yes, well, there's a
multi-machine shuffle.
Yeah.
And you can even get into, once you do even more adventurous things like recursive algorithms, where one node is waiting for the other node, then
for sure, it's
really hairy.
it can get very, very nasty. Yes, Stefan?
You showed kind of the dual interface for the get chunk.
Yeah.
Well, on the single interface, but the dual behavior concerning parallel and non-parallel. Actually, similar, like it's not predefined which operators could be the source or the sink of the pipeline. So basically, there might be operators that are likely to be there, and maybe operators that are never there. But in general, operators could be in the middle or at the sink or source. So in the middle, as you said, you don't need any special treatment because they just act in the pipeline, and their local pipeline if you wish.
Yeah.
But the other ones you do. Do you have this sink source aware implementation for all the operators?
Yeah. So before we just had like sink aware. So because there was no distinction between a source and an operator. And then we would just kind of check, okay, do we know how to parallelize this type of source? If yes, we would do it. Otherwise, we just run it sequentially. But indeed, there was no distinction between a source and an operator. There was already a distinction between a sink and an operator. So we had like a flag in the operator type that would say this, basically. And of course, there's also rules on where an operator can be in a tree, because like a table scan can't have a child again, right? So there are some of these rules. So, but indeed, there's no distinction between a source and an operator, and this is kind of also not very nice. So yeah, a bunch of problems with this. Well, we wanted to switch to push-based execution. So what is push-based execution? Well, our previous model was pull-based. You call get chunk when an operator requires data. Push-based, of course, is the other way around. So the operators, they don't request data anymore when required. They just get data pushed into them, kind of.
And of course, the sync interface, as I mentioned before, that's already push-based, right? Because the sync, you just have a sync method that gets called whenever data is available. So we already had like a kind of a hybrid push-pull-based system. It wasn't fully pull-based anymore in the first place. So it just makes sense to go fully push-based instead of having this sort of odd hybrid with a bunch of hacks. So yeah, push-based, we move the data flow out of the operators, right? So instead of calling the get chunk inside the operator, we have like a central sort of tree that says, okay, this is how the data goes from my one operator to my other operator. That's great. In some sense, it's also part of the goal because it simplifies the implementation of these operators. But it does come at a price, of course, which is the price of flexibility. Before, operators could do whatever they wanted with data. They could just call get chunk here, get chunk there. Whenever they wanted, they could get another chunk. And now we need to centrally define this data flow such that it's like sufficient for all the operators, that it works for all the operators. So that then becomes a prompt to generalize kind of this data flow. So how do we do that? Well, the first step, of course, is to split up this operator and source, because as Stefan noticed before, there was no distinction between operator and source, which is not very nice. So now we have an operator and a source. Well, an operator processes data. So you can think of that like a projection, a filter, a hash probe, whereas a source emits data. So a source is like a table scan, an aggregate hash table scan, order by scan, etc. And you may also notice, I say here, for example, an aggregate hash table scan as a source. Nodes can often be multiple things at once. So for example, a hash join is both a sync and an operator, right? Depending on the position it takes in the plan. So if it's the root of the plan, it's a sync. If it's a like intermediate node, it's an operator. And the pipeline scheduler will take care of setting that up correctly. So that's like, it's called as a sync in that location and as an operator in the other. And an order by is both a sync and a source again, right? So depending on, like, often these things, they serve two purposes. And hash tables actually can be all three: a source, sync, and an operator, join hash tables. So that's even more interesting. I will explain a bit more later. Operator interface, the operator interface is quite simple because there's no, as I said before, operators don't need to be parallelism aware. They just execute, they take an input chunk and they output another chunk. In that sense, it's very similar to the get chunk, except instead of calling the get chunk on the child, we just take it as an input and write the result somewhere to our result. And we have this operator result type that's kind of the main sort of difference. I will expand on that in a bit. So how does that work? Well, in projection, this is very straightforward. You just take your input, you have your result, you just call execute on that. Simple enough. And as you can see, it's much cleaner than the projection was before, right? You don't have to do any data flow. You just run the expressions. That's it. Hash join, hash probe also seems straightforward, at least initially. You just take the input and you probe it and you write to the result. But there's one caveat to the hash probe, which is that the question, how do we handle multiple matches per tuple? Because of course our projection is very clean. We just have one tuple in, one tuple out. A filter is also pretty easy. You have one tuple in, something either 0 to 1 tuples out, like somewhere in between, that can only reduce the cardinality. Of course, a hash join can increase the cardinality, which makes this a bit more interesting, because one input entry can lead to infinitely many output entries. And of course, our result is only still supposed to be like the vector size, right? So these operators, they need a way of signaling that they are not yet done processing the current batch. So they write to the output, but they have more output remaining. Yes?
I claim that the number of output tuples of a hash probe is finite.
Depends on the size of the other hash table, but yes, you...
Quadratic, but okay, that can be a lot.
It's finite, because the hash table is finite size.
Yes, but a hash... Sure, yes, okay. Yes, okay.
It can be.
Yes. Well, okay, no, fine, large, many output entries.
As large as your hash table.
As large as your hash table, yes, for sure. So basically, it can be more than one. operators need a way of signaling that they are not done yet processing this input. And that's what this operator result type is for. So basically the operators, they can return either that they need more input, which is basically, okay, I'm done processing the current chunk. I want a new input chunk. This is basically what most operators will return, right? So like a projection will always return this. A filter will always return this. But a hash probe might not. A hash probe might return they have more output. And that basically means that the operator will need to be called again with the same input chunk before we move on to the next one, right? And then we also have the finished, and that means the operator will not be called again and that the entire pipeline will be terminated. And that's kind of an interesting one. And the reason this one exists, maybe I have this on the next slide. No, the reason the finished exists is because of the limit clause. Because of course, in a pull-based model, your limit just stops pulling when it's done, which is great because you get a limit pushed down. Because if I do a limit 10, my limit pulls one chunk. It notices, okay, I'm done. I'm not going to pull anymore. In a push-based model, you need to signify this flow in a different manner. So you need to say, okay, I'm done processing. The operators need a way of signaling that they are done processing. So that's what this finish node is for. And that also exists in the sync. They also have this. They also have the same return type. They can also just terminate a pipeline early, basically. So the execution loop looks at this result type, and it basically keeps like a stack of in-process operators. And whenever it sees like, hey, this operator has more output remaining, just push onto the stack. And then whenever you want to get more output, you first look at whatever is on top of the stack instead of pulling a new node from the source. Yeah, so this actually, I explained before. Yeah, the finished is just for limits, basically, for nodes where we know, okay, we are already finished. We don't need to keep on processing more tuples. Yeah, okay, so one last note on that. Some operators can reduce the input size, of course, the filter, hash probe, etc. In the worst case, an operator can will only let through one tuple. In a vectorized system, that's not very nice because if you have one tuple flowing through a system all the time, your operators are not built for that. They are not built to process one tuple at a time. Also, engines that are built for that are slow. It's generally not ideal to process one tuple at a time. So what do you do? Well, we have a chunk cache after these operators where basically the operator can signify, hey, I can reduce my input size. So I have this like flag that says, okay, I need a cache. And what the chunk cache does is it checks after one of these operators, what is your output size? If it's less than some threshold, in our case, 64 tuples, if it's below the threshold, we just add to the cache and we keep going to the next chunk. If it is above the threshold, we just directly continue. So we can avoid copying like many tuples, right? Because there is like some cost to assembling these tuples somewhere. And then when the cache is full, we emit the cache. And this has the kind of nice behavior that if you have a filter that only lets through a few tuples every time, you just kind of batch all of that up again immediately after, and you don't propagate it through all your other operators in the pipeline that then get slowed down by it. You just like gather everything and then move on. Yes. So then sources. Well, source interface, in principle, pretty similar to the sync interface. You have a global, you have a local state, because again, the source needs to deal with contention, needs to deal with parallelism. So what happens is we have this get data method, which is very similar to get chunk method, except it's parallelism aware, right? And that get data method is just called until no more data remains, or the pipeline is canceled by like one of the finished nodes, right? So it's still pull-based, the source interface. But it's a lot cleaner because it's parallelism aware. It no longer fetches from other operators. So it's really just like, okay, read a chunk from my CSV file. And one nice thing about keeping the source pull-based, at least for now, is that it allows us to keep the streaming query result behavior, where we can say, okay, if the client only wants to read like one chunk or one row from our result set, even though we are from the back end reading like a giant CSV or Parquet file or table, we don't need to materialize all of that. We can just let the client also consume this stuff chunk-wise. Although there is a minor discussion point later on about the pull-based source interface. All right. Events, yes. So for those that remember the big list I had of problems we had with our system,
union nodes are, of course, very interesting because in the how do we even execute union nodes in a push-based system, right? So suppose I have a sum and I have two union nodes, right? I get this sort of query tree. And when I say union, I mean like union all, right? A union normally is duplicate eliminating, just a union, union all. So basically I have these two scans and they feed both of them directly into the aggregate. In a pool-based system, this is easy because we control the flow, right? We can just say, okay, if we're not done yet with the left child, we pull from the left child. Otherwise, we pull from the right child. So again, easy because in a pool-based system, we can do whatever we want. How do we do it in a push-based system? And how do we do it in parallel? That's also the big question here, of course. So in a push-based union, we kind of notice, hey, we kind of actually just have two pipelines, right? The union, it's no more than just having two pipelines that share the same sink, or more, of course, if you have multiple of them. However, there's one caveat, because the sink is shared, you only want to call the sink after both of these pipelines are done. So it's not exactly like two pipelines because they share the sink. There's a dependency there. So how do you cleanly model that? Well, to do that, we have to look a bit at the pipeline scheduling, how it works. So what we did before was we would schedule the pipelines kind of as is. And if we go back to our previous example, how this would be scheduled is that you have these dependencies between pipelines. So for example, here we have our probe of the hash table. Of course, we can't start probing the hash tables until we finish building them, right? So you have this dependency between these pipelines where the probe depends on both of these things. And what we would do is we would just schedule the entire pipeline, run the finalize, etc. But how do we handle the union? Because the pipeline is basically one block that includes the finalize call. Well, how do we do that? Well, one nice way of doing it is to not schedule the entire pipeline, but to split up the pipeline into events and then schedule those events. So we can take one pipeline and we can split it up into three events. We have the execute pipeline, which does the whole sort of thing like reading from the source, pushing it to the sink. We have the finish event, which calls the sink finalize. And we have the complete event, which just marks the pipeline as completed and moves on to whatever dependents there are. So if we go back to the previous one, well, this is not super readable, but essentially we take these three pipelines and we schedule them now as individual events. And you will see here this dependency still exists, but the dependency exists between the execute, like beginning of the other pipeline, and completing the last pipeline, right? So what do these events allow us to do? Well, with unions, we can now create a dependency on the finalize. So rather than having this finalize be called twice, we can now just have the execute of these two union pipelines scheduled as separate events. And the finalize of this aggregate, the sync finalize, will depend on those executes. So we have two separate executes, and they are kind of like they share a sync, right? So they share the remainder of the pipeline. And any dependencies on this pipeline will then depend on this complete. And you get this kind of nice behavior where you can basically layer as many unions as you want there, right? Like you can execute as much as you want, and you get completely independent pipelines that all lead to the same sync. And that is then nice because now we can do parallelism very easily because we just have a bunch of pipelines that we need to execute. And each of these pipelines internally, these events, they can schedule multiple tasks. They can be run in parallel again, right? So we can run this pipeline in parallel. We can run this pipeline in parallel. We can run this pipeline in parallel. We could even run multiple pipelines at once, like mix and match, like have some threads work on this, have some threads work on that. There's a lot of possibilities there. Now, full right outer joins, they also have a similar challenge. Because, as I mentioned before, we need to scan the hash table after all the probing is finished. What we used to do is just disable all the parallelism there. So in our previous model, we would just check, we just disable the parallelism if there was a full right outer join. And then in the get chunk, we would say, hey, is my probing done? If so, I'm going to scan my hash table for like the remainder of the matches. That works, but again, it's not very nice because well, you have to disable your parallelism just because you have a full right outer join. And that's not great. So how do these events help with that? Well,
the events, now that they're split up, again, we can schedule stuff in between these different events. So if we now have a full outer join, like we have here between the line item and orders table, we can have the execute first that does all the probing. Then we can do a scan of the orders, and then we can do the finalize. And now this event, the scan, can be fully parallelized right after all the probing. So now not only is our hash table probe parallelized, our hash table scan can be parallelized as well, which is of course great. And of course, you can imagine you can layer on multiple full outer joins here, right? You would just get more scans in this sequence before the sync finalize is called. And you can also combine this with like unions with full outer joins to create like a nice mess, let's say, of events. So finally, one other thing the pipeline events are good for is that now we can cleanly solve the scenario where the finalize wants to do more work in parallel. And this happens, for example, in our hash aggregates or in our order by. Because if we have an out of core order, we have like a big merge phase where we want to merge chunks together. And ideally that would all be parallel, right? So, but the sync finalize itself, it's just like, it's called just once, it's called not in parallel. But how we can now solve this problem of doing that in parallel is that we can allow the sync finalize to schedule additional events that happen after the finalize, right? Because this is what schedules the events, but before the complete. And then we can just layer as many events as we want. We can just have like one merge phase, another merge phase, because of course you may not even know how many you need beforehand, right? So you can just, this can be like dynamic. You can just dynamically insert more events before the completion of the pipeline. And the hash table is the same with like the radix partition merges, also works the same way. Yes, so that's the pipeline events. Two more things about the push-based system that are still to do. First is scan sharing. One nice thing about the push-based system, of course, that we can very easily support, well, very easily, we can support scan sharing quite nicely, quite cleanly. Basically, what we would have to do is we detect that pipelines have the same source, and then we can scan the source once and sync it into multiple of these pipelines, right? So for example, if you have like a union between these two aggregates, they both read the line item table. Ideally, we could just read the line item table once and push the data into both of those aggregates at the same time, which would save a lot of time, especially if the table doesn't fit on disk or what have you. The scan sharing, it's slightly complicated by projection and filter pushdown, of course, because if you have two scans, the projections might be slightly disjoint, or they may be slightly disjoint filters. So that makes it a bit more interesting, because when is it worth it to use the scan sharing in those cases? If you have completely disjoint projections, it's probably not useful, except if you're scanning like a CSV file or a row store. So it's kind of like a bit iffy. If you have like overlapping projections, but not entirely, it's kind of an interesting sort of something to look at and benchmark. But of course, in the easy case where everything lines up perfectly, it's certainly useful, right? You just save a scan or multiple scans. And something that's kind of related to this, of course, is duplicate pipeline elimination entirely, because once you're checking that pipelines have the same source, you might as well check, hey, are the pipelines entirely the same? If so, you can just merge them entirely. So that's also a nice sort of bonus of this as well. Then the last point, Async Io. So currently our source nodes, they're pool-based, which is fine for in-memory data. But of course, it means that if we read from disk, from HTTP, etc., the get data, it will still just initiate a read, which means that the execution thread stalls, which is not ideal, because ideally you would want to have interleaved reading from IO and working, right? So one solution to this is Async Io, which basically means you schedule some events when the IO operation completes, push data into the pipeline. And that actually works very nicely with such a push-based system. But of course, our source interface is not handling this, not doing this yet. So we need to rethink the source interface. But then also there's the question, do we always want to do Async Io, or is this like some trade-off? Because of course the Async Io, it does conflict somewhat with like lazy result streaming, lazy vectors. Maybe we should have both Async Io and non-Async Io. It's kind of an interesting question, still open topic.
Then I do not have a final slide. Well, thank you all for attending and listening. I hope it was interesting and happy to take any questions.
Okay. Very interesting. So I have a question. So, I mean, this is great, and I think that you could even, like, now that you have so much control in a central place over the flow, it also that is a very crucial place where you can do nice scheduling decisions and optimizations that are otherwise difficult to do. So yeah, the chunking, the rechunking, the chunk caching is one of the examples, but there is probably more. And the other thing, so I really think this is great, and probably yes, you want to do Async Io always, because you can cast synchronous IO into asynchronous IO very trivially. So, but I was thinking about merge joins. Well, of course, you don't have them yet, but I suppose
we kind of have merge joins, but not the way that Vectorize had them.
Yeah,
but we just resort.
Yeah, like the poster child application of this scan sharing in TPCH. Like there's this query where you join line item on the group by version of line item, and you compare whether the price of an item is higher than the average price of the item in the order, something like that.
Yeah.
So I mean, the perfect way to do that would be scan line item once, and then well, especially if they are, I think they are grouped on order key.
Yeah.
So they, well, suppose that you would know that, then you could do an ordered aggregation, and then you join the result of that ordered aggregation with the line items, and you can scale this in principle in a single kind of sequential flow.
But that's quite difficult, right? Because you have a dependency. Like I can see how this works in, like, if you maybe materialize the scan, of course, but in like a streaming model, it's quite difficult to have because before you can actually handle this comparison with the average, you need to complete the aggregates, right? Which requires a full scan.
I think about states. So like the merge would say, I mean, not only need more data, no, need more data left or need more data right, you know? So because it has two inputs then.
Sure.
And then you could still scale it. And it will turn out to still be perfectly aligned, you know, because you always have, it says left and right, and you always have those two chunks, and you don't need to buffer anything in this case.
Sure. I mean, that would be great indeed, if you don't have to buffer.
But I need to go.
Yes.
Sorry.
No problem. I think there's some other people in a rush. Any more questions from our online audience?
Yeah. Hey, Mark.
Hey.
As you know, I'm looking at inequality joins, and that requires syncing both sides. Does that work in there?
So I'm not super familiar with how you exactly wanted to do it, but I imagine this kind of fits into the event model, right?
Yeah.
Because you have to materialize both sides. So you kind of like, you create two pipelines that go towards the same sync. It's a bit similar to how the union works, right?
Yeah, except you've got to materialize both sides and then sort them, which involves parallelism. And
yeah, sure. But in principle, you just sync, and all you need to do is know which side you're scheduling, right? It's like, oh, now I'm syncing the left side, now I'm syncing the right side.
Okay.
In principle, I think this could fit into this model with like the single sync.
Yeah. Okay.
We'll have to look into it more when you actually like.
Well, I've debugged the paper now. So.
That is good. Any other questions?
Hi, Mark. I also have a question about the events. I think I missed a bit the idea. So the pipeline events, their purpose is to be used whenever there needs to be some type of syncing between parts of the pipeline.
The purpose of the pipelines is to handle like dependency and scheduling, right? The purpose of the events. So at some point you need to say, I will
execute this pipeline after this has been finished, right?
Mm-hmm.
Because you have a dependency of like, oh, my hash table probe depends on my hash table build, for example, right?
Mm-hmm. Yeah.
And of course, we did that before, just scheduling the pipelines. Now the way we do it is to partition these pipelines into 3 different events. And the reason to do that is so we can have more fine-grained control over these dependencies. So that, for example, the finalize is only executed after both input pipelines are done, right?
Mm-hmm.
So that's it. It's just like dependency management on when you get to call which things, when which things run.
Okay, so the difference with the previous part of the presentation, let's say, where you had the example with this one, the hash table with building and probing, is that in this example, you kind of explicitly, let's say, define that probing will take place after building.
Yeah. So that's here. And this is what we used to do. It still happens. So if I actually go to this big slide, this is the old one. And we still have this, but now the pipelines are split into these segments, like these events, right? So we still do the probing after the building, but we have like more events, right? And the reason for that is that we can have more fine-grained control over the dependencies, which is useful for the union, for the full right outer join, etc.
Mm-hmm. Okay, yeah, I get it better now. Thank you.
So for the union, it is because you have a union. Well, in this case, you consider the union all.
Yeah.
And actually, the union itself is no pipeline breaker, right?
The union itself, this is just the union node is just the union all, and SQL union, and this is very confusing, is just a union all with like a distinct on top, right? So this would actually for a union would be the same, but just the sync would be the distinct. Like
no, that's actually not the case, because the SQL union, if I'm not mistaken, takes everything from the first, plus those from the second which are not in the first.
Yes.
It's not distinct because if there are duplicates in the first input, they appear in the output.
No, that's not true. It's a distinct. It's a set operation. I can check this right now. I think it is actually.
You should check the. I'm actually sure that no one has.
I think it is a distinct.
I think so too.
No. 2-1 in Postgres. No, it's Postgres.
Oh, it's Postgres.
I believe Postgres on the standard. Oh, sorry, this the people can't see.
Oh, sorry, then I was saying I thought it was.
No. Yes, we have checked the Postgres implementation on that. Sorry, the people online can't see my shell.
Okay.
Hey, Mark.
Yes, sorry, Richard, go.
Yeah, I can't hear when people are talking. Sorry if someone else is already.
No, it's fine. We will pick it up.
So what's the difference between pipeline events and, say, mini operators like lollipops or something? It seems like you've basically taken a traditional operator and then pulled out the different micro operator pieces of it and had that scheduled as events or something.
It's not entirely similar. So it's kind of related, right? Because you split one operator into multiple pieces. I think the lollipops are a bit different though, because I'm not entirely, don't recall the details, but I think they schedule like the parts of the operator. Right? They schedule like, okay, now it's scheduled order, now it's scheduled window, right? Whereas our composition, we still just run the operator once. The only thing we decompose is the execute and the finalize and like the complete. So we don't decompose the semantics of the operator.
Right.
When to schedule the finalize.
Yeah, but I mean, the operator itself does that. That's what I'm saying.
Yes, the operator itself will actually run the thing, right? Yeah. Yes, Stefan.
Yeah, actually, picking up where I was about it, and a bit in the same way what we should just ask, what you explained about it, because in the original pool-based model, is this single pipeline versus multiple pipeline? Because now you have this pipeline, but you don't have it out of the pipeline. If it's a single pipeline, you get like one final line, one complete, one final line, one execute, but you get two executes.
So
two inputs to the
in the
inputs to the pipeline.
in the pool-based model, a union would just disable parallelism, and we would just have one pipeline that involves this union node, this one here,
Yeah, okay.
which just pulls from both sides. So you would have one pipeline that has multiple sources, and then because that's difficult to parallelize, we just didn't parallelize it. So
And now you have two pipelines, but
we have two pipelines, but they share the sync, and they are kind of special because they share the finalizer, right?
Yeah.
Yeah.
Okay.
Hans?
Yeah, just I think this general discussion about async versus non-async. We talked about this some time ago. There's just two arguments. One is the lazy vectors, which I totally get. If you have lazy vectors, you have lazy vectors, and if you're push-based, you can't be lazy because there's no way.
You just get data. I mean, you can maybe hack it in there somehow, I suppose.
You could have.
Yeah.
You could leave data untouched.
Unread,
Yeah, or like you just remember where it is.
Yes.
Like a buffer, and then.
Just remember, when I touch this, now I need to schedule another event or something like that.
Which will get you somewhere, right? I mean, with Parquet files, for example, I can totally see how that could work because the file's not going to go anywhere.
Yes.
The lazy result streaming, I'm also wondering because you could do something like you have this watermark where
you need resumable pipelines.
Exactly.
Yeah.
So what is the thing that's stopping you there, or is there?
I think just implementing it as well.
I mean, in general, is there any fundamental reason why you say, because yes, indeed, you do need resumable pipelines because you don't.
I think with resumable pipelines, you do get the lazy result streaming. I think the main sort of conflict would be the lazy vectors, because for that I can you kind of, the whole point of lazy vectors is that you need at will IO, right? You need to say, I don't read from disk until my system signifies that I need it. Sometimes that's useless, sometimes that's very useful. That's kind of the whole question mark there, right? You don't actually know. But if you don't have an interface that supports, now I need to read from disk at whatever function call, you can't really support lazy vectors. Yeah. So that's kind of the whole conflict I see there. Indeed, lazy result stream you can just solve by having resumable pipelines. I think that's not a big showstopper, let's say.
Yeah, I think in the end then it comes down whether lazy vectors are worth.
Yeah.
Right. And I think we also had some question marks on the on how portable the async is, right?
Yes, for sure. I mean,
also...
well, the thing is you can model async IO kind of as threads, right? Where you just have threads reading from disk. You don't necessarily need to use like the IO U-ring stuff or something like that. You can just have, which I think a lot of systems do have as well. You can just have like IO threads and worker threads. But yes, that's also from an implementation perspective, definitely a question there.
So what do you think is what's the trade-off there?
I think we probably want to have async IO because it's quite necessary for any HTTPS related stuff. The question is, do we want to have, I think the main question then becomes, do we want to have lazy vectors? How do you implement that? I don't know. Right.
I think it both seems like a nightmare to me.
Yes, probably.
Just my impression.
Oh, the thing is you can have async, if you have worker threads, you can have async IO by just having a worker thread called the get data, or like the IO thread called the get data and then pushing that. But I don't know. It's yes, probably it will be a nightmare. Yes. So
thank you.
Mark, I have one question. In hash probing, when you talked about the state where you need more more data has to be processed, like third state where it needs to it still has some data left.
Yes.
So in that case, I am confused on how the it won't go to the next input data chunk because it still needs to.
Yeah.
So how will the mapping work across these vectors?
What do you mean with the mapping?
So I was thinking that if like if we have the results in the form of, let's say, columns or chunks, if we like, would we end up having, let's say, a one-to-one mapping or one-to this serial mapping of results?
I'm not quite sure I understand. So what the hash join does when it says that there's more matches remaining, it will just get called again with the same input and probably return more rows, right? So that's kind of the whole sort of idea there, is that you just say, okay, I want to be called again with the same input. It does return all the same columns, right? So there will be like one tuple, there will just be more tuples going out, right? Because a join can just change the amount of tuples you have.
But then if it gets the same input, how will it know to, like, this amount of input has already been processed?
There's a state there. So there's just a state on the process. So if you go back to the operator interface, there's just an operator state, and the hash join knows how to handle that, and the other joins as well, right?
One question: to handle all these states, like for the pipelines, you reusing the same pipeline object that you had before in the other?
We still have the pipeline object, but we now have the pipeline executor that holds the actual execution state for one thread, right? So that's where all the local states live, all the intermediates and such. So one kind of change there, of course, that now all these intermediate vectors and such, the intermediate chunks, they live inside the pipeline executor instead of inside the operator states, right? Because the operator states are not concerned anymore with the intermediates of previous operators of children, etc.
Okay.
So it's now all in a very centralized location.
So if for instance, if the probe is not done, then it will feed with another chunk to the probe, and the pipeline takes time.
Yeah, and that will all happen in the pipeline executor. Yes. All right. Then if there are no more questions, I wish everyone a nice weekend, and thank you for listening.
Thank you for the talk.
Well,
Very nice.
Thank you.
Thank you, Mark.
Thank you.
Thanks,
Bye.
Mark.
Have a nice weekend.
Have a
You
nice
too. See you, everyone.
See you.
Clarifying.